In this video, we are going to talk about lightweight management of resource-constrained sensor devices in Internet of Things. A research paper done by Sheng, Wang, Changchuan, Xiping, Shusen, and Victor C.M. Leung, which gives a co-app-based device management solution to allow easy access and management of IPv6 sensor devices. The concept of Internet of Things, popularly known as IoT, can be traced back to the pioneering work done by Kevin Ashton in 1999, and it is initially linked to the new idea of using RF identification, popularly known as RFID, in supply chain. Since recently, this term became popular and is well known as a new communication system where the Internet is connected to the physical world via ubiquitous wireless sensor networks, also known as WSN. Generally, sensing devices are with common features of constrained energy resources, limited processing capability, vulnerable radio conditions, real-time nature of applications, and no direct human interaction. By interconnecting sensor devices using low-cost wireless communication technologies, which is usually named as WSN, a new ecosystem with a large number of smart applications has been formed. With the development of IoT technologies in past few years, a number of major standardization alliances are gradually formed based on their interest in technology selections and commercial markets. Technically speaking, current IoT solutions can be categorized as non-Internet protocols based and Internet protocol based solutions. Most of the off-the-shelf solutions belong to the former, especially some well-known standard alliances such as Zigbee and Wave2M for office and manufacturing automation, and Wireless Heart and Profibus for real-time industrial control systems. However, most of these non-IP solutions are isolated within their own verticals, which hinders the IoT development due to the incompatible nature across heterogeneous communication systems. Motivated by the fact that the Transmission Control Protocol (TCP) or IP protocol is the de facto standard for computer communications in today's networked world, IP-based solution could be the future of IoT networks. IP Smart Object Alliance, also known as IPSO, actively promotes IPv6 embedded devices for machine-to-machine applications. Profinet, a promising real-time Ethernet standard, also adapts Ethernet to the next generation of industrial automation. In order to tackle the technical challenges, such as extensive protocol overheads against memory and computational limitations of sensor devices, Internet Engineering Task Force (IETF) takes the lead to standardize communication protocols for resource-constrained devices and develop a number of IP, including IPv6 over low-power wireless personal area networks, also known as 6LoWPAN, routing protocol for low-power and lossy network, also known as RPL, and constrained application protocol, also known as CoAP. Although a wide range of intelligent and tiny sensing devices have been massively deployed in a variety of application environments, many open challenges remain, which are mostly due to the complex deployment characteristics of such systems and the stringent requirements imposed by various services wishing to make use of such complex systems. In order to well maintain a large scale of WSNs, for example, dynamic registration of sensor devices or monitoring sensor performance, IoT device management, also known as DM, authorities should be able to provide a reliable and efficient way to remotely monitor and control sensor devices without consuming significant resources. This also provides a motivation to recent global IoT M2M related standardizations. In particular, the One M2M Global Initiative has been formed to develop one globally agreed specifications for common service layer, which can be the basis of horizontal management platform. The IoT-A project, which is a European research project addressing the reference model of IoT, is to develop IoT architectures in an interoperable manner. The project has derived entities and resources which are subject for management functions and provides various functions to orchestrate and manage collaborations of IoT devices.
Device management is an integration of network, system, and application managements. In essence, it includes provisioning and management, configuration of network parameters, firmware upgrades, and performance monitoring. As a result, a number of device management standards are emerging, such as TR069 for automatic configuration of set-top box, ISO or IEC 145433 for home and building automation, and field device integration for the unified management for all field devices. The problem that now arises is that none of these standards can be directly used on IoT devices, especially on a low processing and battery restricted sensor device. So the researchers looked at open technologies to tackle device management of wireless sensor networks and found the IPv6 based solution a promising one. Motivated by the fact that the COAP is an application layer protocol which is intended for use in resource constrained internet devices and the simple network management protocol, they proposed a framework of CoAP based device management solution for wireless sensor networks and developed device management oriented functions, resource identities, and protocol. Specifically, an approach is taken to extend the REST paradigm, in which a lightweight web server can be embedded in resource-constrained sensor devices and map device management functions into CoAP methods. In essence, the proposed method not only integrates IoT into the network but also manages them via the web. A considerable research has been done on different aspects of sensor networks, but the management issue for sensor devices is still little explored. Although there are recent works considering to introduce management into CoAP server, they all either build management capabilities on top of CoAP or need to support multiple protocols simultaneously, which may bring extra overhead for resource-constrained devices. In short, the authors have tried to develop an efficient and lightweight device management solution by extending the CoAP protocol without consuming extra resources. Before we move to the solution, we would like to introduce the IEEE protocol stack used in resource-constrained networks. The figure on the screen illustrates the protocol stack ranging from physical layer at the bottom up to the application layer on the top. Now, let us look at the various layers of the stack. IEEE 802.15.4 is a radio technology standard for low power and low data rate applications with a radio coverage of only a few meters. It has typically a maximum data range of 250 kilobyte per second and a maximum output power of 1 milliwatt. The maximum packet size is only 127 bytes. In order to achieve energy savings, the radio transceiver must be switched off when there is no traffic but switched on when the communication is engaged. Next, let us look at 6LoWPAN. The main focus of 6LoWPAN is on protocol optimization of IPv6 over networks using IEEE 802.15.4. There are two reasons to apply 6LoWPAN over the IEEE protocol. Firstly, consider that the maximum frame size supported by the IEEE protocol is only 127 bytes and the payload size available for the application layer is also very limited. Secondly, since the minimum value of maximum transmission unit specified by IPv6 is 1280 bytes, which is larger than that supported size of IEEE protocol. Next, we shall look at the routing protocol. RPL is a distance vector routing protocol in which nodes construct a destination-oriented acyclic graph by exchanging distance vectors and route information with a controller. Finally, let us look at the CoAP protocol. CoAP is a specialized web transfer protocol for resource-constrained nodes and networks. CoAP confronts to the REST-style architecture. It abstracts all objects in the network as resources. In order to ensure reliable transmission, CoAP introduces a two-layer structure as shown in the figure. The message layer is used to deal with asynchronous interactions with UDP, such as conformable, non-conformable, acknowledgement, and reset messages. Whereas the request or response interaction layer is used to transmit resource operation requests and request or response data. Nextly, we would like to introduce the proposed framework of the efficient device management solution for WSN based on IETF Open Standard CoAP protocol. First, let us look at the management functions. The system architecture in the figure shown shows the interaction between an IoT client and a sensor device. It especially shows the device components interfaces to IoT client. 5 major device management functions which are applicable to the WSN have been proposed. First, registration. It is a primary function to allow a sensor device to register or deregister with a remote management server to maintain and update registration information. 2. Provisioning. It is to initialize and synchronize essential information of a sensor device with a remote management server. Third is management services. Once the sensor device is connected with a remote server, a number of essential management services should take in charge to maintain IoT services. Fourth is observing. It is the unique feature of CoAP to allow sensor devices to observe resources. That is, to retrieve a representation of a resource and keep this representation updated by the remote server over a period of time. Fifth is the application data transmission. The application data transmission includes any application data that can be collected and delivered to IoT clients or any other application protocols above CoAP. The interactions with IoT client can be directly triggered with these resources via get, put, post, and delete methods provided by CoAP. Now we are going to look at the second aspect of our framework, naming and addressing of resource identities. We define a simple resource model in which resources are logically organized into class. A class defines a group of resources. Example, the hardware class contains all the resources that can be used for provisioning purposes. A resource is identified by the following path. The class ID, resource ID, and sub-resource ID are with size of 1 byte. The method ID is 4 bits, and each bit from the most significant bit represents an authorized operation. The value 1 means authorized, and the value 0 means unauthorized. The table shown below shows the detailed naming and addressing assignment to the resources on our sensor testbed. Finally, let us look at CoAP-based management protocol. The proposed device management protocol is fully based on IETF-defined CoAP protocol with newly defined resources identities to identify management resources and mappings of CoAP methods to management functions. The CoAP is based on the exchange of short messages which by default are transported over UDP. The message format starts with a fixed size 4-byte header. This is followed by a variable length token value which can be between 0 and 8 bytes long. Following the token value comes a sequence of 0 or more CoAP options in type length value format, optionally followed by a payload which takes up the rest of the datagram. Thus, the RESTful approach provided by CoAP protocol can be adopted as a lightweight method to access from application servers to wireless sensor devices. Now that we have established our IETF protocol stack and the proposed framework of the efficient device management solution, let us look at the evaluation of the presented solution.
Now we are going to discuss about the prototype system that describes the implementation of the RESTful device management method to IPv6 wireless sensor networks. The network topology is shown in the figure, where the laptop shown here acts as a client to retrieve sensor resources via the router, which acts as a RESTful gateway. In order to show the implementation, the sensor nodes are deployed to monitor indoor environment. The sensor platform is equipped with IEEE 802.15.4 compliant radio transceivers, and in order to support IPv6 connectivity, all sensor devices are running Quantigi version 2.6 operating system with implementation of 6LoWPAN, IPv6 and RPL protocol based on IEEE 802.15.4. The sensor devices communicate with each other and the RESTful gateway using CoAP over 6LoWPAN, which is shown in the diagram, thus forming an 15.4 wireless sensor network area. The gateway converts the CoAP messages to corresponding HTTP messages and sends to the user device over IP network. The figure shows how the interaction process using HC proxy happens. Each layer specifically describes certain functionality. The libcoap layer defines message structure and methods to implement CoAP message layers based on UDP. CoAP request response layer encapsulates the data structure and methods relevant to CoAP requests and responses. It is to transmit CoAP request in the form of CoAP message through the message layer and generate CoAP responses based on received CoAP messages. The HTTP CoAP mapping layer is used to implement mapping from HTTP request to CoAP request and vice versa. That is, when converting a HTTP request to a CoAP request, the HC proxy needs to convert the HTTP request method, URL, header, option, and payload respectively. If a proxy encounters an error, it has to generate corresponding error responses. Now we will discuss about the gateway for the implementation. In order to have negotiations between internet devices which cannot understand CoAP and devices which transmit CoAP packets over the air, a gateway is being used here. The IEEE 802.15.4 connectivity is being integrated with Open Platform Gateway for having connection between router and the sensor nodes or devices. To have access from an ordinary IP terminal to an IPv6 sensor device, the operating system of the gateway OpenWRT is ported with HTTP CoAP proxy or HC proxy, which is shown in the diagram. The HC proxy is implemented using libcoap, which is an open source implementation of CoAP and conforms to GPL version 2 or higher licenses for the CoAP protocol. Now we will discuss about the working of the RESTful gateway. The HTTP client sends the HTTP request over TCP IPv4 or IPv6 network. The HTTP CoAP mapping layer, as mentioned previously, converts received HTTP request into corresponding CoAP requests. The CoAP request response layer converts corresponding requests to CoAP messages and sends them to CoAP server over UDP IPv6 network. The request is then processed and then transferred back to HTTP client in the same manner. Now we will discuss about the performance evaluation of the proposed system. The evaluation results will illustrate the performance of the proposed CoAP-based DM solution and its application in the IoT system. The configuration of the system for the evaluation is being described in the figure. This is the same figure shown before for the prototype. The HC proxy gateway and the sensor devices are connected wirelessly via IEEE 802.15.4 and using channel 26. The laptop client is connected to the gateway through the Wi-Fi channel. The network topology as shown in figure is built with a maximum 2 hops where the camera sensor and humidity and temperature sensor are connected to the gateway with 1 hop distance. Now we will talk about the latency performance of the CoAP protocol for device management solutions. In order to manage a large-scale deployment of WSN, it is necessary to keep the protocol overhead as small as possible. In this evaluation, we compare the round-trip time between CoAP ping to a sensor node, Internet Control Message Protocol, ICMP ping message to baud router, and ICMP ping message to sensor node. Using Linux 6 commands, the Quantity Mac is configured as no sleep mode. The IPv6 packet size is fixed as 52 bytes in the sensor devices. The graph shows the comparison between the 3 types of RTT discussed. The RTT of the border router using ICMP are 49.75 ms and sensor node is 79.54 ms, and the average RTT of CoAP ping to sensor node is 80.5 ms. It is clearly noted that the RTT to the sensor node is much higher than that of the border router. This is because of the processing time imposed at the gateway as well as 1 extra hop to transmit to the sensor node. RTT of CoAP ping is very close to the ICMP ping to the same sensor node, which only claims a 1.2% increase. Thus, the result shows that the overhead imposed by CoAP protocol is negligible, and thus the CoAP-based DM is a promising solution for IoT. Next is we compare the packet length of the proposed CoAP solution with the standard CoAP solution. The uniform resource identifier, that is URI length, is calculated and compared for the packet comparison method. The standard URI format for the onboard resource is as follows, and the proposed URI format for the onboard resource is as follows. It is clear that the proposed URI representation takes far less memory space than the standard URI representation, in which the main space is consumed by the attributes. Through the resource discovery get, we can receive a response with a list of available resources in a particular CoAP related sensor device, and the total length of the transmission packets for both methods is 420 and 109 bytes respectively. Since the CoAP response will be transmitted in a blockwise fashion, the standard method takes 6 blocks whereas the proposed method only takes 2 blocks. The memory saving of 311 bytes is composed of URI savings and 4 extra CoAP block headers. The total transmitting packets can be reduced by 74%. In order to evaluate the performance of a large-scale network, another test is performed to evaluate the packet loss rate in a multi-hop environment. The test is carried out in an open office area with strong Wi-Fi background noise and lowest possible WSN radio frequency output power to ensure a multi-hop fashion, which makes a sensor device that can only communicate to each other within around 30 centimeters. The sensor devices are with only 8 KB RAM and 256 KB flash. A maximum number of 6 hops can be obtained by optimizing the communication system. To retrieve the same onboard resources, get requests operations are done over the same number of measurements. Table shows the packet loss rate in a multi-hop network. From the table, we can see that there is an increase in packet loss rate with the dramatical increase in number of hops because of severe environmental interference and channel congestions, etc. Moreover, additional configurations to ensure a multi-hop transmissions, one-way communications, and low output power also contribute to the high loss. However, the result does not affect the truth that the proposed solution is always achieving better performance than the standard method.
In the conclusion, we would like to say that the authors have proposed a CoAP-based DM solution and developed a prototype system to implement some basic functions on IPv6 sensor nodes by integrating IEEE 802.15.4 connectivity and HTTP CoAP proxy into an open platform gateway. The remote access and management from an internet device to an IPv6 sensor device can be realized in a unified manner. Through the performance evaluations, they have shown the simplicity and efficiency of the proposed solution, which is promising to drive IoT development. Thanks for watching the video. If you have any questions, you can find us at the following email IDs.